Hello, good afternoon, good morning, whenever you're watching this. Today, R1's lesson, we're going to talk about sets and number systems, okay? So what we're looking at here is the different number systems that we have. The first one I'm going to talk about on top is what we call counting numbers. The smallest counting number is 1. Counting numbers are also called natural numbers. But then we have 2, 3, ... meaning it goes up forever. Let's see what's not belonging to this set. We don't have 0, we don't have any negatives, and we don't have any numbers between 1 and 2, 2 and 3, so no fractions in between those counting numbers. All right, the next set that I want to talk about is whole numbers. Whole numbers start with 0, then we have 1, 2, 3, ... The only difference between whole numbers and counting numbers is we include 0. Okay, still no numbers in between 1 and 2, 2 and 3, no negatives, but it goes on infinitely. So all of these sets that we're talking about have an infinite amount of numbers or elements, so we would describe them as infinite sets. Now, the next set of numbers would be called integers. The only thing that integers are going to include that whole numbers don't have is negative numbers. This one goes to the left forever because you can see the ... to the left, right? The ... to the right. So all the way to negative infinity, all the way to positive infinity, but still no fractions in between each one of the numbers, right? Okay, another thing I want to talk about is when sets exist in another set, there's a symbol for that. But if you look at counting numbers, since all counting numbers are also whole numbers, you could say the counting number set exists in the whole number set. The whole number set exists in the integers. Okay, now rational numbers is any number that can be written as a fraction with integers on top and bottom, or as a decimal that terminates like 0.25, which would be the same as 1/4, or repeats like 1/3 would be a fraction, but if you wrote that as a decimal, it'd be 0.33333 repeating. So those numbers are rational numbers. Now, all integers and whole numbers and counting numbers exist in the rational numbers set, because 3, like for example, 3 can be written as a fraction, it would be 3/1, and as a decimal that repeats, it would be 3.0. So, the next set that I want to talk about is kind of off to the side because none of these will exist in the next set, and none of the numbers in the next set would exist in this one, so they're different, and that's irrational numbers. So irrational numbers as a decimal don't terminate and don't repeat. Okay, and can you think of a number that when written as a decimal goes on forever and ever and ever with no sort of pattern, no repetition? There's a famous one, it's pi. So one example of an irrational number would be pi. I think another one would be like radical 7, because radical 7 or square root of 7 is not a perfect square when simplified. It doesn't simplify to a whole number or a counting number. It's a decimal that goes on forever and ever and ever with no pattern. So for now, the only irrational, there's more types, but the only irrational numbers we're gonna really focus on is pi and radicals that do not simplify. Those would not be rational numbers or belong to any of the other sets that we've talked about, but all of these numbers, both irrational and all of the first sets that we talk about, we would also lump them into a set called real numbers. Later on in the class, we're going to get into complex or imaginary numbers, but all of these numbers today that we talk about are real numbers. Now we're going to look at some notation. Notation, guys, is just a way that we write things. So we're going to look at some notation for sets. I'm going to make some sets here. I'm going to make this set U is equal to, let's say, 1, 2, 3, 4, 5. So notice for set U, there's no dot, dot, dot on either side. What that means is that, I'm sorry about this 5, I'm going to rewrite it. I'm terribly nervous to be on camera. But there's no dot, dot, dot on either side, meaning it doesn't go on infinitely. So this is not an infinite set. This is what we would describe as a finite set with 5, it has 5 elements. If you can count the number of elements in the set, it's finite. So I'm going to make a smaller set, A, and that's going to be, I'm going to say that one's 1, 2, and 3. We could say A exists in U because every element in A belongs to set U. My other set that I'm going to use is B. And I'm going to say set B is, let's say it's 2, 3, and 4. What do you think? Does B exist in set U? It does. Does U exist in set B? No, because not every number of U belongs to set B. There's a symbol for exists, guys. And the symbol that we're going to use for exists is this. I would say that A exists, it's like this little kind of funny looking E, in U. And that would be a true statement. If a set does not exist in another set, one way to write it, like we know that A does not exist in set B because there's numbers that aren't in both. So one thing I could say is A does not exist in B. So this is the symbol for does not exist. Let's look at some other symbols. The next symbol I want to look at is like an upside down U. That is a symbol for intersect. So an intersection is when elements exist in two different sets. So if I said, find the intersection of, let's do an example of an intersection, of A and intersected with U. So A intersected with U means we're going to try to find all the elements or numbers that exist in both sets. Well, let's see, I see 1, 2, and 3 here, and I see 1, 2, and 3. So the numbers that both sets share would be equal to 1, 2, and 3. This is fun. Drawing these little squigglies is fun. Now, if there's no sort of intersection, if there's no elements that exist in both sets, which could be the case, we call it an empty set, and this is a symbol for an empty set. Okay? Let's do another symbol. This right side up U, that's what we call a union. Okay? A union is a set that's formed by any element that exists in either set. So I want to find, for an example, let's find A union with B. Okay? So that for union, if it's in either of the two sets, then we're gonna include it in our union set. Okay, so do we have a 1 in either set? Yes, we do. Do we have a 2? We have a 2 in both, but since it exists in either set and it's a union, we're gonna count that in the union. There is a 3, and there is a 4 in the B set, so we will also count that number. So the A union with B set would equal 1, 2, 3, and 4. Okay, I'm looking forward to this lesson because it's kind of different, and there's going to be some exploration on your own. So good luck with it. If you have any questions, email me, and I'm excited to hear about how you did. Thank you all very much.